A little bit about Charles' law here, okay? Charles' law is like Charlie Brown, okay? Where do you watch Charlie Brown?
TV.
On the TV. So Charles' law is going to be the relationship between temperature and volume. So looking at your notes there, you have some pictures of some balloons on front, okay? On the left-hand side,
So we know it's not velocity.
you could if you want to, okay? Perfectly fine with me, okay? All right. On the left-hand side, if we take and increase the temperature, we take a balloon and we put it in the microwave. What's going to happen to the balloon? It's going to eventually pop, but before it pops, what's going to happen? The volume is going to get larger, okay? So Charles' law, temperature goes up. What happens to the volume? Volume goes up, okay?
So
Now,
Charles, they both go up?
Charles, they both go up. That's
So
right.
if they both go down, one goes down, the other goes down.
So if temperature goes down, volume goes down.
So that's the freezer.
That's a little bit of the freezer, okay?
The temperature goes down.
On a Coke
No,
or
just
on like a balloon. If you stuck a
Yeah.
balloon in the freezer,
That's like
okay?
when you leave a basketball outside in the winter, it gets all shrunken.
Exactly. It's why during the winter you have to check the air on your tires. Okay? If you leave your bicycle in the garage and you haven't ridden your bicycle for a couple of weeks, temperature gets cold and you go out there and look and your tires look flat. It's because the temperature went down, so the volume of the tire went down. Okay? All right? So there's a direct relationship there. Okay? One goes up, the other one goes up. One goes down, the other one goes down. All right? So you need to be sure you understand that relationship. So let's look at our formula. All right? Now I'm going to teach you the formula in one way using the Boyle's Law formula. Okay? So this is our new formula. P1 V1 over T1 equals P2 V2 over
So this is Charles
T2. This is Charles and Boyle's Law together.
together.
But we're going to talk
PV,
about,
TV.
all right, PVT. All right? Now, is pressure mentioned at all in this equation right here? No, so you're making the assumption that what? That the pressure has not changed. So if the pressure hasn't changed, can we eliminate that factor?
Yes.
So what do we end up with for Charles' law? V1 over T1 equals V2 over T2. Okay? Oh, I messed up, Ryan.
The only one I can't remember is Bernoulli. What did he do?
Bernoulli is fast-moving fluids. Why the ping pong ball floated on the air.
Oh.
Fast speed, low pressure. High speed, okay. High pressure, okay. All right, so let's look at our new page here. So Charles' law. T1 over V1. That's not right either. Okay. V1 over T1 equals V2 over T2. Now, a little caveat here. Temperature must be
Kelvin?
in Kelvin.
Why can't we just use Fahrenheit?
Because Fahrenheit has and here's the why. The reason is Fahrenheit has a negative scale, Celsius has a negative scale. Okay?
Kelvin will have.
Kelvin doesn't have a negative, it has an absolute starting point. So all we're looking for is the change in temperature. Okay? So we need to know that
I think everybody should switch back to
degrees Celsius
Fahrenheit.
plus 273. All right? So if I told you the temperature was 20 degrees Celsius, what is that in Kelvin?
293.
So it would be 20 plus 273 would give us an answer of 293 Kelvin. So on these problems using Charles' law, if I give you a temperature in Celsius, add 273. If I give you the temperature in Kelvin, you just go ahead and solve the question. Okay? So temperature is going to be expressed in Kelvin. Yes, Ryan?
What if you give us the temperature in Fahrenheit?
I won't ever give you a temperature in Fahrenheit and ask you to convert it.
What's the relationship between Kelvin and Celsius? Is plus
plus 273. And the real difference is, here's 0, okay? That would be 0 Kelvin, all right? That would be negative 273 degrees Celsius, okay? And if you go up to 10 Kelvin,
Because isn't Kelvin's the one that's based off like absolutely no particles move?
right, exactly right. That's called absolute zero, where nothing moves, not even an atom or an electron. Okay? This here, so we would take and add 10 degrees to that. So that would be negative 263. Okay? Does that make sense? All right? So let's look at our sample problem. Look on the bottom of your notes down there. Okay? It says at 275 degrees Kelvin, an air-filled balloon has a volume of 200 liters. If the pressure of the air remains constant, what will its volume be at 300 degrees Kelvin? So let's write down what we know. V1, T1, V2, T2. The hard part is going to be when you start to solve questions now is trying to decide, do I use pascals, do I use boils, do I use Kelvin? So I think this step right here is going to become very important in helping you solve questions. Okay? What is our volume number 1 in this question? 200 liters. And our T1, 275 degrees Kelvin. V2. We don't know V2, so I'm going to represent it with X. And T2, 300 what? Degrees Kelvin. So let's look at my formula. V1 over T1 equals V2 over T2. Alright? So let's plug our values in.
But couldn't you just put it as an equation like 200 times 275 equals...
You could do
X
that.
times 300?
Okay? You could definitely do that, and it's perfectly alright. Okay, 200 liters over 275 degrees Kelvin equals X over 300 degrees Kelvin. Now, Caitlin, to answer your question, my first step is going to be what? Cross multiply, correct? Does that give us what you just said?
Yeah.
Okay, so I'm going to say 275 degrees Kelvin times X equals 200 liters times 300 degrees Kelvin. So how would I solve now?
Multiply 200 times.
Divide by 275 degrees Kelvin. Divide by 275 degrees Kelvin. That cancels. Degrees Kelvin cancels. So we say 200 times 300, which is 60,000. And then 60,000 divided by 275 gives us an answer of X equals 218.18 what?
Liter.
Liters. Okay?